In this lesson, we're going to learn how to use L'Hopital's rule, which you may see it spelled with an S or without an S. That S is silent. It's named after the French mathematician that came up with this process, and I understand that the best pronunciation is L'Hopital's. So our learning target is to apply L'Hopital's rule to limits of an indeterminate form. It might surprise you that we're going back to studying limits because we started the year in Unit 1 learning how to solve limits. But L'Hopital's rule involves the process of using derivatives to simplify limits. And at that point in the year, we hadn't learned all the rules and tools that we need to find derivatives. But now that we have, we can circle back and learn how to use L'Hopital's rule as well. It's going to determine the limit of a quotient of two functions that produces an indeterminate form. And we talked about this indeterminate form earlier this year, but let me remind you, it's defined as a non-numeric expression such as 0 over 0 or infinity over infinity. So before now, when we got an answer, or when we got this result, because we won't call it an answer, we had to keep using other means such as factoring or reducing until we got a value that's an accepted number or infinity. So these are not known values that we can leave as a final answer. So they happen when we use substitution to evaluate a limit, and when they happen, we can now use L'Hopital's instead of the algebraic skills we were practicing earlier this year. So a couple of years ago, just for fun, when we started learning about L'Hopital's, I used to call these boo-boos because they have a lot of O's in them, and it was just kind of a cute thing to remember. And we talked about where do you go when you have a boo-boo? Well, you go to the hospital. So kind of a cheesy little thing, but it might help you remember when you get one of these indeterminate values to go directly to L'Hopital's rule. So let's take a look at what L'Hopital's rule tells us that we can do to solve these indeterminate limits. So if f and g are both differentiable, so that's a requirement for using L'Hopital's, that both of the functions must be differentiable or able to take the derivative of, then the limit of the quotient of f and g is actually equal to the limit of the quotient of f and g derivatives. So I want to make a really important note here, and that when we do L'Hopital's rule, we're going to take the derivative of the numerator and denominator separately. So we'll just take their derivatives and create a quotient of them. I don't want this to be confused with the quotient rule. This is a different process, and we will not use the quotient rule. I can see where students might make that mistake because it looks like a quotient, but we actually are using a different process to find a limit. So we'll take the derivatives separately. I'd like to walk you through a quick proof of L'Hopital's rule, and that is when you're taking the limit of the quotient of two functions, you can go ahead and subtract f of c and g of c, because we're saying that for these two functions, when I substitute c for f and g, I get that 0 over 0 indeterminate form. So if both of those values are 0, I'm not changing the value of the expression by subtracting 0 in both the numerator and denominator. What I did next to both the numerator and denominator was I divided them by x minus c, which is legal because we did it to the numerator and denominator at the same time. So really we're just dividing or multiplying by 1. And then I hope that you recognize in both the numerator and denominator, we now have the specific definition of the derivative. And so those expressions both go to f prime and g prime respectively. So that takes us from the limit of the quotient of f and g is equal to the limit of the quotient of f prime and g prime, which is exactly what L'Hopital's rule states. It's important to recognize when we can use L'Hopital's and when we don't need to use L'Hopital's. So I've created the first two examples that are really similar to each other. They just have one difference in the denominator, and that difference will make the choice of whether we need to use L'Hopital's or not. So as with any algebraic limit, our first strategy is to substitute that limit value for x. We get 3 squared minus 9 over 3 plus 3. When I simplify, I see that I get 0 in my numerator and 6 in my denominator, and that is not one of our indeterminate forms or our boo-boos. So we're able to come up with a finite answer or a definite answer of 0 over 6, which 0 divided by any number is going to equal 0. So that's our final answer. So this is a really straightforward example that shows algebraic substitution sometimes works, and you don't need to resort to another strategy like L'Hopital's rule. I just wanted to give you a quick reminder of what the values are going to equal when you see only one zero in the numerator or denominator, but not both. So if you have 0 over a number, we'll say that's okay, and that equals 0. If you have a number over 0, that's not okay, and it gives you an undefined value. So we look at the second example, which is really similar to the first. I only changed the sign of the denominator. We're going to see something completely different happen. So we will start with the same strategy of substitution. So our 3 goes in for x in both the numerator and denominator. And we have to use some foresight here because I can see quickly that I'm getting 0 over 0, which is an indeterminate value. I am not allowed to write equals here. I wanted to switch to another color to make a dramatic point. So since 0 over 0 and infinity over infinity are considered non-numeric values, or they have no value, I can never attach an equal sign to a non-numeric value. So I have to show very distinctly that this expression doesn't necessarily equal 0 over 0, but it goes to 0 over 0. So you're going to have to train yourself to remember to put an arrow instead of an equals between an expression and an indeterminate form. That's really important because it's something that you will miss a point for on the AP exam. So it's a little technicality, but really important. So once I determined that I get the indeterminate form, or the boo-boo, I realized straight away that my next strategy is to go to the hospital, or L'Hopital's. So I'm going to recopy my limit as x goes to 3. And now to apply L'Hopital's, we're going to look at the numerator and denominator and take those derivatives separately. So the numerator derivative will be 2x, and the denominator derivative will be 1. So notice that is not quotient rule. We took those derivatives separately. And so once we have that expression, 2x is a much simpler thing to substitute into. So we will try to substitute again. So 2x equals 2 times 3. So our final answer for this problem is 6. As we start the third example, we're going to start with our first strategy, which is always to substitute our limit value. We get a square root of 4 minus 2 over 4 minus 4. And thinking ahead really quick, I do see that I'm going to get a 0 in both the numerator and denominator. So I don't want to write equals. I'm going to write that it goes to 0, 0. And so I'm going to need to rethink and go ahead and try L'Hopital's rule on this instead. So L'Hopital's tells us to copy our limit as x goes to 4, take the derivative of the numerator, and I know that square root of x is x to the 1/2. So power rule gives me 1/2 x to the negative 1/2. The derivative of the denominator x minus 4 is 1. I'm going to simplify and go ahead and try to resubstitute my 4. So 1/2 times 4 to the negative 1/2. The negative gives us the reciprocal of 4. The half square roots it. So we end up with 1 over the square root of 4, which is 2, 1 over 2, times the half that we already had gives us a final answer of 1/4. So you may have noticed this first row of examples are all things that we already knew how to solve using algebra. The first two could have been easily factored. The third one I would have had to use the conjugate, which is not always our best friend. So in certain situations, factoring may be easier for you, but in other situations, L'Hopital's might be a better choice. So it's just another tool in our toolbox. In contrast, the second row of examples are ones that cannot be simplified algebraically, and L'Hopital's would be the only and best route to take. So for example, when I'm looking at the limit as x goes to 0 of tangent x over 2x, I do try to substitute my 0. I get tangent of 0 over 2 times 0. Both of those values go to 0, so my limit is indeterminate. But this is not something that I can factor or use the conjugate for, so L'Hopital's is my only choice. So my next step is to apply L'Hopital's. My limit as x goes to 0 is now going to be the quotient of the two derivatives. So my numerator derivative of tangent x is secant squared x. My denominator derivative of 2x is 2. So let's go ahead and try to resubstitute the 0. To find the secant squared, I find the 1 over cosine at 0, which is 1, so 1 over 1. I do need to square it. It still gives me 1 over 2, so 1/2 is final answer. We'll pick up here when I see you in class.